Let's talk about dual spaces. So suppose V is a vector space over a field F. Now recall that we could look at V and view that as a vector space over itself. And so we can consider a linear transformation from V to F. And such a linear transformation is called a linear functional, or functional for short. And the dual space of the vector space V, it's denoted V star. This is the vector space of linear functionals on the space V. So in this Hom notation, V star is just F linear homomorphisms from V to F. So for example, if V is R2 and the field is the reals, then I could define a linear functional phi1 that goes from R2 to R, and given an input xy, it's going to output x, so the first coordinate, the first component of that vector. Similarly, I could define a phi2 that's outputting the second component. And now the claim is that phi1, phi2 is a basis for the dual space of R2. Right, so this is called a dual basis. You should check by hand that this is a basis for V star as an exercise, and we'll talk more about dual bases in a second. So suppose V is a finite-dimensional vector space. Then the claim here is the dimension of V is equal to the dimension of V star. Now given what we've discussed so far, the proof is actually very short. So the dimension of V star, just by definition, is the dimension of the space of F linear homomorphisms from V to F. And recall from last time, as long as you're willing to pick a basis for the vector spaces involved, you can identify these spaces of F linear homomorphisms with matrix spaces. And so this is exactly equal to the dimension of the space of matrices that are 1 by n, if n is the dimension of the vector space V. And so that tells you that the dimension is equal to exactly V, the dimension of V. All right, so now suppose I fix a concrete basis for my finite-dimensional vector space V. So B is going to be V1, V2, up to Vn. I'm going to define functionals, f sub I. These are functionals that are defined by fi of Vj is delta ij. So this is the Kronecker delta symbol. So it's equal to 1 if I equals j and 0 otherwise. And so I'm going to use that to define fi of Vj for j equals 1, 2, 3, all the way up to n. And so I've defined fi on a basis, which from an earlier theorem means we can extend it in a unique way by linearity. Right? So these fi's are going to be linear transformations where all I've done is tell you what it does to a basis, but we're extending by linearity, and so you get f1, f2, all the way up to fn. You'll get n linear functionals on V. So the fi is called the ith coordinate function, and if I collect all of those functions, all of those coordinate functions together, I get what's called the dual basis of B. So we still need to check that this name suits the set, right? So right now it's just a set of functionals, and we need to check that B star is actually a basis for V star. So let's check that now. So the claim is that B star is a basis for V star, keeping the notation from the last slide. So here's the proof. So first notice that the dimension of V star is equal to the dimension of V, which is n, since we have an explicit basis for V with n elements. And so since B star has the same number of elements, it's enough to show that B star generates V star, and that'll be enough to show that it's a basis. So let me take a generic functional f, and I'm going to write down this expression, and I claim that f is exactly equal to this expression. So I claim that f of x is, I'm going to take f of v1, that'll be some scalar, and multiply that by the functional f1. plus f of v2 times the functional f2, all the way up to f of vn, and then multiply that by the functional fn. Right? And I claim that that linear combination of the functionals is exactly equal to f. So how can we check this? Well, just notice that fi of vj is delta ij, right? These are the coordinate functions. And so the right-hand side, when I evaluate it at vj, I get exactly f of vj, right? Because fi of vj is going to be 0 unless I equals j. And this is going to be true for j equals 1, 2, all the way up to n. And so then, we're going to extend by linearity, and the theorem says there's a unique way to extend it. And so since both sides of this expression are linear transformations, by uniqueness, the right-hand side has to equal the left-hand side. So what have we done? Well, we've expressed a generic functional as a linear combination of these coordinate functionals, right? So a linear combination of the b star, and so we've shown that b star generates v star. Since we know that the dimension of b star is n, that's enough to show that b star is a basis for v star. And that completes the proof.